third equation is Faraday's law, which is integral of E vector dot ds vector should be equal to d phi b upon dt. So in order to use this equation in a loop, let us say that we are taking a loop in xy plane. So this is x, this is y, and we take this loop. Okay, and let's say that the loop is being traversed in this direction, and electric field is in this direction, and the magnetic field is in this direction. So if the electric field is a function of x at this point, electric field will be a function of x plus dx, because this distance will be, if this distance is dx, and if the length of this loop is L, then when we move from one point to the other, the electric field will change for this loop and this loop. And so let us say that we are talking about this loop, and let's say this line is A, this is B, this edge is C, and this edge is D. Okay, so integral of E vector dot ds vector will actually be integral over A plus integral over B integral over C integral over D. So integral over A will be actually 0, because here the electric field, whatever the value might be, it is perpendicular to the loop. So that is why integral this quantity, it will be equal to 0. So we write 0 plus. Now over B, so it will be, electric field is along y-axis, displacement is also along y-axis, so it will be E into ds cosine of 0 plus over C, it will be 0 because the length is along this axis and electric field is along y-axis, so they are perpendicular to each other, so it will be 0 plus integral over D. So length is downwards, electric field is upwards, cosine of 180 degrees, so it will be electric field ds cosine of 180 degrees. But now I have missed something, and that is the electric field is, because electric field is changing at both of these points. So for B, this is for B and this is for D. For B it should be electric field is a function of x plus dx and ds plus integral of D, and for D the electric field is a function of x and ds, and because of 180 you should get a negative sign here. So then we can also write it as, because now electric field at a constant on all of this length, it will be constant, but it varies with x, but at a particular x it will be constant, so we can also take it outside, and then it will be integral of ds plus or minus. Here also we can take it outside because it will be constant, so it will be integral of ds. So what we get from here is x plus dx into L, because total integration over these lengths will be L, minus ex into L. So now this is a function of x plus dx and this is a function of x. So we need to remember that if you have a function which is a function of x plus dx, then it could be written as f of x plus curly f upon curly x into dx. It can be written like this. Okay. So when we use it here, this total integral is E vector dot ds vector. So then E vector dot ds vector will become Ex plus curly E upon curly x dx. We are not talking about t here because t will be, let's say we're talking about a particular time t. Okay, so we're not talking about t here. So this will be for this term into L minus E of x into L. Okay, so we've used this expansion for this term and this is what we get. So E of x into L plus L dx curly E upon curly x minus Ex into L. So you can cancel these and it will be L dx curly E upon curly x. This will be E vector dot ds vector. Okay. Let's say this is equation 1. Now let's try to find out the left hand side for this equation. So for the right hand side we have calculated, and what we got is E vector dot ds vector is equal to L dx curly E upon curly x. Okay. And we are calling this as equation 1. Now let's try to find out the magnetic flux. So the magnetic flux will be, now on this entire area the magnetic flux will be along the z-axis, which is perpendicular to this entire area. So we can also write it as B of into area, so it will be B into L dx, because this total the magnetic flux will be given by BL dx, and therefore now if we take a derivative of this, it will be d upon dt of B to L dx. Let's say this is equation 2, and this was our original equation. So let us put these values in this one, and therefore it will be L dx curly E upon curly x will be equal to L dx curly B upon curly t. But we are missing something here, and that is a negative sign. So you will have to put a negative sign here, and therefore this will cancel, and what you will get is curly E upon curly x is equal to curly B upon curly t. Let us say this is equation 3. So now let's try to use the fourth Maxwell's equation, and we are taking this loop for this Maxwell's equation, and we'll try to use this equation to get an equation from that. So if you've taken this loop, this is x, this is y, and this is z, and let us say that this distance is dx, and that is why we are taking magnetic field to be x plus dx, and the length of the loop be L. So now let's again divide it into 4 parts. So let us 1, 2, 3 and 4 parts of this loop which are taken separately. So integral of p vector dot ds vector will actually be an integration over 1 over 2 over 3 and over 4. So now let's talk about one by one. So for length 1, you know that the magnetic field is along z direction, so it will be Bz, and it is a function of x and t. So here the magnetic field will be along the z direction. So for length 1, magnetic field is in the positive z direction, but we are taking the length to be in the negative z direction, so they are opposite to each other. So we can write it as B. Now the magnetic field along this length will be Bx plus dx, and then the length is L, and then the angle between them should be 180 degrees. Why? Because length is pointing in this direction and magnetic field is pointing in the z direction, so they are pointing opposite to each other. So this was for length 1. Then let's talk about length 2. For length 2, you know that the magnetic field is perpendicular. Now magnetic field will be perpendicular to length, so it will be B ds cosine of 90. Integral of 3. So for 3, the length is along positive z direction, magnetic field is also along positive z direction, so both of them, they are in the same direction. So, and the magnetic field at this point is P of x, because along the whole of this line magnetic field will be constant, so it will be of x. ds will be the length is L cosine of 0, because magnetic field and the length vector, they are in the same direction, so magnetic field is in this direction, length is along this direction. But for 1, they were opposite. Length was in this direction, magnetic field was in this direction, so they were opposite to each other. So then we come to length 4. For 4 also angle will be 90 degrees, so it will be 0. So we get rid of 2 and 4, so what we are left with is minus L. Then we have to remove this integral because I have already taken ds to be L. So let's remove this integral, okay, because we have already taken integral of ds to be L. Okay, this L is actually integral of ds. So integral of ds is equal to L for 1 and also for 3. Okay, so this is what we have used. So then this turns out to be minus L b of x plus dx plus L b of x. Okay. And now you know that this could be opened as fx plus dx is equal to fx plus curly f upon curly x dx. So we can write it as minus L b x plus curly b upon curly x dx plus L b of x. So this term and this term will cancel, and what we are left with is this. So this is the left hand side of the equation. Now let's try to find out what is the electric flux. So in order to find the electric flux, the total electric field through this area is perpendicular. So this area is on the plane and the electric field is perpendicular to the plane, because this is XZ plane, and so it will be like this, and so the electric field will be perpendicular to the plane. Okay, so it will be EA, so electric field and area will be LdX. So then let's say this is equation 4 and equation 5, and now put equation 4 and 5 in the fourth Maxwell's equation. What we get is minus LdX curly B upon curly X is equal to mu naught epsilon naught upon curly T of ELdX. So this equation then turns out to be minus LdX curly B upon curly X is equal to mu naught epsilon naught LdX is equal LdX curly E upon curly T. So we can get rid of LdX, and what we are left with is curly B upon curly X is equal to minus mu naught epsilon naught curly E upon curly T. So this is the final equation we get from fourth Maxwell's equation. And there was another equation, which is equation 3, which was curly E upon curly X is equal to minus curly B upon curly T. So now we're going to use these two equations and try to find out the final result. So now we have these two equations, and now let's say that we take this equation and we take a partial derivative with respect to x. So we take curly upon curly X of this, and also on the other side, so it will be curly B upon curly T. So we can also write it as curly square E upon curly X square is equal to minus curly upon curly T curly B upon curly X. So let's replace curly B upon curly X from here. So it will be curly upon curly T minus mu naught epsilon naught curly E upon curly T. So then this equation becomes curly square E upon curly X square will be equal to mu naught epsilon naught curly square E upon curly T square. Now if we see this equation and we compare it with the wave equation, if you remember this was the wave equation and it had this solution. Okay, so now if we compare these two, then now the wave equation, general wave equation is curly square y curly x square is equal to 1 upon v square curly square y upon curly t square. So this is your general wave equation. Okay, and it has a solution which is y is equal to a sine kx minus omega t. So this is the solution for this equation. So now when we compare these two equations, what we find out is that the velocity of the electric field will be 1 upon v square will be equal to mu naught epsilon naught. When we compare these two, this term is actually should be equal to 1 upon v square, and therefore v will be equal to 1 upon mu naught epsilon naught under root, and this comes out to be 3 into 10 raised to the power 8 meters per second, and this is known as the velocity of light. So it means that the electromagnetic wave is moving with the velocity of light. Similarly, let us try to find an equation for magnetic field. So now let's say that we take the derivative of the other equation, and let's say we take a derivative of this equation. So it will be curly upon curly x of curly upon curly x of curly b upon curly x is equal to minus mu naught epsilon naught curly upon curly x of curly e upon curly t. Okay, so we are just taking a partial derivative of this equation with respect to x. So it will be curly upon curly x of this minus mu naught epsilon naught curly upon curly x of this. So this equation becomes curly square b upon curly x square is equal to minus mu naught epsilon naught. Let's exchange t and x, so it will be curly upon curly t and curly e upon curly x. Okay, now we know what curly e upon curly x is. Let's replace this equation. So it will be minus mu naught epsilon naught curly upon curly t of minus curly b upon curly t. So it will become mu naught epsilon naught curly square b upon curly t square, and left hand side was curly square b upon curly x square. So this equation is exactly similar to this equation. So it is a wave equation for magnetic field, wave equation for electric field, and if you compare this will again be equal to 1 upon v square, so it will come out to be c. So now this equation has this solution. So the solution for the wave equation for electric field will be, when we compare this to this equation and the solution. So if this is the equation, then if this has this solution, then this equation will have a solution where E will be equal to E maximum sine kx minus omega t. In the similar manner, the equation for the magnetic field will have a solution where B is equal to B maximum sine kx minus omega t. So this is entirely on comparison. This is this solution, it will have this solution, this will have this solution. So this is the solution of this equation. Okay, so then where k is 2 pi upon lambda, omega is 2 pi upon t, omega upon k will be 2 pi upon t divided by 2 pi upon lambda will be equal to lambda upon t. Now lambda upon t is actually equal to v, so omega upon k will be equal to v, because this will be equal to v. So this will give you, now in case of electromagnetic waves, we know that the velocity is the velocity of light, so it will be equal to, so velocity of light, so omega upon k will be equal to c, so which implies that omega upon k will be equal to c. And now let's say that we divide the solutions which the electric field wave equation and the magnetic field wave equation have. So when we divide, let's say this is now 1 and this is 2, so divide 1 and 2, that will give you E upon B will be equal to E maximum upon B maximum. And if now we use another equation, which was, let us say we use this equation, which is curly E upon curly X is equal to minus curly B upon curly T. And let us put the value of E and B, where you know E should be equal to E maximum sine kx minus omega t, and B is equal to B maximum sine kx minus omega t. So when we take a derivative of E with respect to x, it will be k E maximum sine kx minus omega t, cosine kx minus omega t, and curly B upon curly t will be minus omega B maximum cosine kx minus omega t. So now just put these two in this equation, and what you will get is k into E maximum is equal to plus omega B maximum, which means that E maximum upon B maximum will be equal to omega upon k, and we know that omega upon k is equal to c, so this should be equal to c. Therefore E maximum upon B maximum is equal to E upon B, which we have already calculated from here. So it will be equal to C. You can also remember this. Okay, that's all.